Good day, everyone. We'll start. Today, I will give you two more examples. I hope I do have time. Okay. But before that, I would like to discuss a few issues in connection with dynamic programming. We have seen quite a few examples on Monday. So I believe all of you have an idea what a dynamic programming algorithm look like. There are a few important issues. All right. So let's see. So let me first discuss four important issues in connection with dynamic programming. In examples we discussed on Monday, we're just looking for optimal values instead of an optimal solution. So natural question is how do we find an optimal solution and instead of just the optimal value? Because eventually that's what we want to obtain. So I will first discuss how we find optimal solution instead of just optimal value. Second thing is we use bottom-up approach to compute the recurrence relation. So can we actually do it top-down? Which can we use recursion directly? But we need to avoid overlapping problems. So we don't want to repeatedly computing overlapping problems over and over again. Actually, it can be done. It's called a memorization. So I will discuss that part. And thirdly, what kind of problem are suitable for dynamic programming? There are some requirements. One is very similar, actually it's the same as the structure for for greedy method. It's called optimal substructure. I will also discuss this one. And then I will make a comparison with divide and conquer because divide and conquer is also algorithm based on recurrence. So what's the difference between divide and conquer and dynamic programming? So I discuss these four issues first, give example for these four issues, and then we'll give you two more examples of dynamic programming. All right? Okay. So let me start with optimal solution. So let's use the shortest path problem as an example. In a deck. So let's use this problem for example. So we can define distance and we obtain a recurrence relation. So if we order vertices topologically, V1, V2, so suppose vertices are ordered. That's topological sorting of the graph. All right. Then we have recurrence relation, D, say V, maybe I use J instead of I. Okay. In notes, I use VI, but same thing, okay. Because ordering IJ, it's natural ordering, maybe weight of VI, VJ. So VI, VJ is an edge. Okay. Okay, so here dVj is shorthand for distance from starting vertex and Vj. All right, so typically maybe starting vertex V1. All right, so that's the recurrence relation we obtain. So, but this one only compute distance. So it computes the distance. That's a value. But actually what we need to find is shortest path. Shortest. Oh, sorry, so it's S, not VI. Because starting vertex is S. That's what we need to find actual path. So how can we find such a path, actual path, instead of just the value? All right. Actually, it's very simple. What we need to do is do some bookkeeping in the process. Some bookkeeping. So what we need to know is when we compute dvj, so what happens is vj, so it's come from some vertex. So here, look, it says here the minimum. So it's come from some vertex. All right. So suppose it's come from this vertex. V maybe use I star. Yeah. Okay. Okay. So the minimum if come from this particular vertex. So what we need to do is just remember where it come from. So actually what we happens is we add this edge. All right. So let's use P of a vertex, so Pj, Vj equal the vertex where we use it for shortest path. So that's parent of Vj. All right. So parent of Vj. All right. So that's a vertex Vi star such which minimizes this relation. So which minimize this relation. So it's dvi plus wvi vj. So what we need to do is just remember this vertex. Then we can trace it back. From this vj, we can trace it back, find actual shortest path. So that's the same as what we have done for Dijkstra algorithm. Okay. So for example, in the graph, if eventually we have the following in a graph, maybe I still draw on this page. So some edges from left to right, okay. All right, so for each vertex, we have this value. That will be computed when we compute d of v, all right? So for each vertex, we have such value. So then we can trace it back. For example, for this vertex, if it's vertex, maybe this one. So we can trace it back. We know we use this edge. Now for this vertex, again, it has a vertex as its parent. So maybe this vertex, so we can trace it back. All right. So this one maybe just starting vertex, and we trace it back. So afterwards, we use this information, we can find the actual path. So this actual path can be found. All right. So it's very simple. When we do bookkeeping, just remember where do we get the optimal value. So basic idea is remember where we get optimal value. Also keep this information when we compute the optimal value. So then afterwards, we can trace it back. All right. So that applies to the homework problem, the last problem for subset sum. You can use same idea. All right. So that's how we do bookkeeping in order to find optimal solution instead of optimal value. All right. So that's quite simple. Okay. Okay. So next thing we discuss is how can we compute recurrence in top-down approach. So then we get second one, memorization. So what we want is to compute the recurrence instead of bottom up. We want to do it top down, but avoiding repetition. So is it possible? Actually, we have seen it. It is possible. For example, when we use divide-conquer method, divide-conquer is top-down approach. It's dealing with recurrence. So sometimes it can be done. But here, typically when we do dynamic programming, there are overlapping sub-problems. So if we do it in this way, it will be very, very inefficient. So what we want to do is we try to avoid repetition, but we want to do it in top-down approach. Actually, it's very easy. It can be done. For example, let's take a look at Fibonacci number again. So we really want to do it in this way. So is it possible? Because last time we showed, because the repetition say F6, then F5, F4, F4, F3, here F3, F2. We see that some things are repeated. So that's what we try to avoid. So actually, it can be easily resolved by a very simple trick. Very, very simple trick. The first time when we want to compute a value, we do it. But next time when we want to compute the same value, we'll check whether this value has been computed already. If it's computed already, we don't recompute it. So for example, maybe we go to this branch first. So this one will be computed. So then maybe perhaps we maintain an array. So in it, maintain an array to indicate the value have been computed already or not. 1, 2, 3, 4, 5, 5, 6, so on. All right. If it's computed, we mark it. So next time when we want to compute F4, we check whether 4 is marked or not. If it's marked, so that means the value is there already. We just use that value. Okay. So Fibonacci number. So 4 is stored here already. So we can just use that number. Do not need to recompute it. But first time we'll compute it. So that's very, very simple trick. That's called the memorization. So if you look at the actual implementation of recursion, what happens when we use stack? So F6 is put into a stack, right, in order to compute it. So it will be replaced by F4, F5. All right. So F4 then will be replaced by F3, maybe F2, F3. Sorry. F2, F3. So stack changes in this way. So F4. Yes, it's better to use animations, and you can no need to change it in this way. So F2 then will be changed to F0, F1. All right. Now each time when it pop out from the stack, we check whether it's this value here, whether it's marked or not. If it's marked, we just use the value. If not, we extend it. All right. So for 0 it's done, so we can just take out. So this one out maybe. Okay. F3, if value is there, so now it's there, it's also computed. It's on it. So we can just take it off. All right. So here, if next one there are F6 here, so original F6 is replaced by F4 and F5, right? No, actually, no, I should not write it should be F7 actually. So it should be F7 because then I'm talking about F8. F6 is replaced already, F7. All right. So 5, this one will be computed. So that means all these values are computed already. Now when I do F5, it becomes F5, F6. Or actually 6 is computed here already. So I can check because both of these two are computed already. I do not need to recompute them. So that's the idea of memorization. All right. So if we make a difference, a comparison between top-down approach and the bottom-up approach, both have there are a trade-off between these two methods. Top-down actually is better in terms of the number of sub-problems we need to solve, because it's only solve sub-problems that are needed. If it's not needed, we will not solve it again and again. So let me show you an example. Say the binomial coefficient Mn. All right. So we have this Yang-Hui triangle. You need to draw a little bit large, otherwise to finish too quick. All right. Now, in order to say I want to compute C, C, 1, 2, 3, 4, 5, 6. I think it's 6, 2. All right. So in order to compute C62, if I use top-down approach, in this picture, actually, sorry, if I use bottom-up approach, so in this picture, actually looks like bottom-down because the triangle is in this way. Otherwise, triangle will be reversed. All right. So this bottom-up, this is called the bottom-up. All right. Just as we talk about trees, normally when we draw trees, actually we draw tree in this way, but it's should be other way around because it's a root. All right. So it's bottom up actually it's this way, right? Okay. So when we want to compute this number, actually we need to compute every increase in this way. So level by level. So we compute first layer, second layer, and so on. But if we use memorization, all right. So actually here, choose two, right? It's here. So what we need is starting with this one, just consider Z2 and this one. So it only computes parts of it. So this only computes this part. Other parts will not be needed to be computed. So in terms of number of subproblems solved, actually saves time because does not need to solve all subproblems. But the other catch, a recursion, actually it's overhead, it's costly, overhead for recursion. Because we use memorization, we use a stack to implement recursion. So overhead actually is higher. So whether it saves time or not really depends. So it's solve less subproblem, but because of overhead for recursion, so actual time it may take actually maybe even more than the bottom-up approach. So memorization is this way, okay? So top down, it's really upside down here. All right. So really, there's a trade-off. Depends on the actual problem. It may be better to do it in bottom-up manner or do it in top-down manner. But there is a simple way to resolve the repetition of overlapping problems. So that's called memorization. Okay. All right. So that's the second issue. To avoid the repetition of computation, we can use memorization. But remember the overhead, it may not worth it. Really depends in terms of actual running time. So we have to be careful in actual use of memorization. We have really to be very careful. All right. Okay. Now, third issue. So in order for dynamic programming to work, it's essential that a solution All right. So solution for an instance can be obtained from solution to its sub-instances, or you can say solution for a problem can be obtained from solution to its sub-problems. So that's very important. So that's allow us to be able to obtain a solution from solution of its sub-instances. So typically we deal with optimal solutions. So here is optimal. Typically when we say solution, we say it's optimal solution. Minimization or maximization. So maximum value can be obtained the maximum value of sub-instances. Minimum value can be obtained of minimum values of sub-instances. It's the same for grid method. And it's essential for dynamic programming. Without it, we cannot do it. Because with this one, we only need to keep solutions, optimal solutions for sub-instances. We don't need to keep all possible valuable solutions. So the suboptimal solution, we do not need to keep it. Because if we keep all of them, the number of solutions may be too many. So in a sense, dynamic programming is just, I will give you an example in a minute. Okay, dynamic programming is just a smart way of exhaustive search. In a sense, dynamic programming typically in a reduced search space. All right. So let me give you some example about this point. All right. So let me use the well-known example of shortest path. All right. For shortest path, actually we can have write V. So dV denotes distance from S to vertex V. All right, so that's shortest path. For shortest path problem, this distance always obeys this recurrence relation. So here we're dealing with minimization problem. So here is this one is minimum, this one is minimum. A shortest path has the optimal substructure problem property. So if you, no, it's a pen. Okay. All right. So suppose we have shortest path. P is shortest UV path. All right. Then it goes through some vertex, say W. Then this part, say let's call it P1. Then this part P2. Then what it means is P1, P2 are all shortest paths. So P1 is UW path. P2 is WV path. Okay. So that's what we mean by optimal substructure. So we do have this one. All right. Okay. So that's for shortest path. Now be careful why dictionary algorithm works when edges have no negative cycle. When edges no negative edges, and said otherwise we need to use Bellman font if there are negative edges. But when it has no negative cycle, what's the reason behind it? We see that it has optimal substructure. Why it may work and may not work, even we have same recurrence relation. All right, so let's take a look at this one. Let's also explain why dictionary algorithm works. Now, this recurrence actually it's a kind of subtle. We need to be careful when we talk about distance. Definition of distance, we defined it as length of shortest path. When we define distance, all right, length of shortest path. But actually, we're kind of abusing it. Actually, it does not really mean path. Because when we say path in graph theory, actually it should mean simple path. So that means no repetition of vertices or edges. But actually, this one does not hold. And simple path, actually, this one does not hold. It only holds when actually what we mean by path is walk. We can repeat vertices and edges. It's called a walk. If we just say simple path, actually, this one does not hold. So I'll leave it to you to think it over, okay? So it does not really hold when path really means a simple path. Now, the reason dictionary algorithm works actually is when edges have no negative weight, if no negative edges. When it has no negative edges, this one always holds. So actually the walk become a path because there are no point to repeat edges more than once because edge weights are, if positive or no negative, there are no point at all. So this one always holds with no negative edges. All right. Now, even under that condition, how can we compute it using this recurrence is another question. As I mentioned earlier, every dynamic programming has an underlying DAG. They are the underlying DAG. Now, in order to use this recurrence relation, we want to have a DAG so we can compute these values with respect to this DAG, say from left to right. All right. So how can we do it? So we need actually to order vertices so that we can compute this relation according to this ordering. Dictionary algorithm allow us to do so because it defines an implicit ordering of vertices with respect to the following. Let's see. So there, sometimes you really have to think deep in order to understand everything. To understand more, okay, not everything. I think understand more. So V1, V2, V, and so on. So dictionary algorithm, when we discuss it, we say it's a greedy algorithm, but actually we can also regard it as a dynamic programming. Actually, I think there is no point to classify an actual algorithm into a particular method. Not much point at all. But we can say that use some ideas. These ideas just helping us to obtain algorithms. Okay. Whether it's really should be classified as this particular algorithm, a particular method or not, actually it's not important at all. Right? But anyway, we can regard it as dynamic programming. Now, what's underlying DAG? Dictionary algorithm actually use the following as underlying DAG. So at any moment, we have a shortest path tree. That's a partial tree. So starting from S, we have a shortest path tree at any moment. So that's part of vertices that have been visited. All right. So the ordering of vertices is with respect to T. So next vertex is a vertex closest to T. So that's why what happens when we use dictionary algorithm. The vertex, we add it to S, this vertex with minimum delta value. So actually, that's a vertex closest to T. So actually, Dijkstra algorithm compute the distance according to this ordering. Because of this ordering, we're able to determine distance. All right. Now, why it does not work when there are negative side and negative edges? When there are negative edges, when there are presence of negative edges, Dijkstra algorithm does not work, may fail to work. When there are negative edges, the reason is this particular ordering does not work. Actually, there exists ordering, but this ordering is not easy to compute. When there are negative edges, the ordering actually we can order versi with respect to their distance, but this ordering is exactly what we want to compute. So without knowing this one, actually we cannot find a good ordering. So when negative edges, we cannot have a ordering for Dijkstra algorithm to work. So you can say that. You can say this. Or maybe, sorry, instead of saying that's a DAG, so that particular DAG does not work because if we have negative edge, say 3, maybe 5, but if they are negative edge, so if we compute distance with respect to this ordering, actually it's not good because when we compute distance, we put it 1. But actually distance is better, maybe actually this is not because it's better, actually we do it in this way. All right, so actual distance is -7. So with respect to this ordering, it's not good to compute this distance information. So that's why Dijkstra algorithm works. Does not work when there are negative cycle, negative edge. Of course, when negative cycle, it fails. All right. So there are subtlety here. No, no. When we see DAG, actually, the whole graph is not a DAG. But when we compute it, we ignore these back edges. So this DAG defined by Dijkstra algorithm, we only consider the forward edges. They are the backward edges. So these will not be in the DAG because when edge weights are positive, we just ignore them. That's a DAG implicitly defined by Dijkstra algorithm. So we have a linear ordering, but slow with these back edges, we get a DAG. All right. Okay, so see there are subtlety here. Now, the other problem is that the optimal structure does not hold. For example, instead of shortest path, let's consider longest path. All right, longest path. Or maybe undirected one. Let's just use undirected one. No need for direct one here. Hey. So let me redraw it. Suddenly I lost one line. So we're looking for longest ST path. All right, so it's too easy to see because this graph is very simple. So longest path is this one. All right, okay. Now if we consider this vertex, what's the longest? So in this path, the path is of length only 5. So this part is only length 5, but what's the longest SX path? So actual distance is 20. So this one is the longest one. So longest path problem does not have this optimal substructure problem. All right, because solution of the sub-solution of a longest path itself is not a good solution. So we cannot use it for the longest path. All right. Now, we may think about the consideration for longest path. So we see the shortest path. So perhaps say, let's see, so use big D. All right. So perhaps we do have this one, dV, du, okay, dV, yeah. Maximum. All right. So we can have a relation, the consideration for long length or longest path. It's use same idea, minimum, shortest path. Right? It's very easy, very simple, but actually it does not work. So this one actually does not work because path, so really need to be a simple path here. Again, it does not hold. This relation does not hold. Because eventually, the length of the path we obtain, it's not a path. This one only gives us a walk. So this recurrence relation does not hold at all. Because inside we repeat vertices and edges. So we cannot use it to solve the longest path problem. But for DAG, it works. This one works for DAG. All right. Okay. So that gives you an idea of the importance of substructure and optimal substructure in a problem. Now, the key part, one of the key parts of dynamic programming is to identify sub-problems in connection with this one. But actually, it's not that simple. What are sub-problems or sub-instances? Because it really heavily depends on this one. Typically, there are sub-common example or template. For example, if input sequence is x1, x2, x3, x4, x5, xn, typically type of subproblem. One is the first I element. The first I element as a subproblem. So that number of subproblems will be linear. For example, the subset sum problem we discussed. All right. The longest subsequence, the increasing subsequence problem, a DAG, longest path, shortest path, or longest path in a DAG. All of them have this type of subproblem. We use this part as subproblem. But sometimes maybe it's better to use some problem, maybe not just the first k element, but just a consecutive sequence, this type. So a consecutive I elements as a subproblem, but then the number of subproblem will be n squared. I don't think we had a discussion example for this one, but textbook can contain a few examples. For example, chained matrix multiplication in the textbook. So that one use consecutive ones as a subproblem. So that's the thing that's a little bit more complicated. All right. So typically, we use this type of subproblem. It's not trivial, but there are some template. For example, on trees, if we have a tree, typically we use subtree as subproblem. So that's subproblem. So inside, if you enlarge it, inside it's also look like this. So then we use these as subproblem and so on. Okay, there will be one example about this one. I don't think I have time to discuss these two examples. I will see what I will do. Okay, so that's the third issue. The fourth one is I want to make a comparison with the divide and conquer. Because divide and conquer also dealing with the recurrence, but we use divide and conquer and dynamic programming. This one is top down. This one bottom up. Of course, we can use memorization. It's also top down. All right, from dynamic programming. And divide and conquer typically recurrence is we relate Tn with T alpha n. So alpha is less than 1. Typically, that's what we do, maybe half. So T half of n. So recurrence relation have something like this. But in dynamic programming, recurrence we get very often it's Tn in connection with T maybe n minus 1 or Tn minus some constant. So it's different. So the reason divide conquer works very quickly is because this reduction, because the reduced size of instance a lot. So that's why it's very quick. Even there may involve some overlapping subproblems. But for dynamic program in the recurrence relation, reduction of the instance size is very small. So overlapping problem really cause a great amount of trouble. All right. So let's see one example I want to, let me give you one example. The Fibonacci number again. So Fibonacci number again, let's consider Fibonacci number again to illustrate the idea. So we can do Fibonacci number, compute the Fibonacci number based on the following recurrence relation. So it's in homework 1, I think, right? So that's the recurrence relation. And then if odd, all right. So we can compute Fibonacci number, use this recurrence relation, use divide and conquer, because 2n will be reduced to n minus 1. Here 2n minus 1, the size n minus 1. Okay. But actually, when we use divide and conquer, there are a lot of overlappings. Subproblem overlapped. Subproblem really overlaps. Okay, because here we do fn and fn minus 1 separately. When we do them separately, there may be overlapping problems, but it does not affect the complex too much because the reason is it's reduced from 2n to n minus 1 to about half. So it's reduced about, problem size are reduced by half. So because this one, so top-down approach is okay. All right. So I want to make a comparison between divide conquer and dynamic program. You see the subtlety, and that's the reason why we can use divide conquer. Sometimes even we have recurrence relation, top-down approach does not work because of overlapping. So that's the reason. So this one not very good for top-down approach. So therefore, we need to use bottom-up approach. All right. So these are 4 important issues involved in dynamic programming. There are 2 more examples I want to discuss. I maybe have to, today I don't think I have time for these 2. Maybe on Monday or just give a short lecture for that. I will record it. I will decide either Monday or I do a short lecture. That way, if I do it quickly, 15 minutes at least. Slowly half an hour. It depends. Okay. All right. So I think that's it. Before I finish, I think I want to mention one thing about homework 3. Homework 3, exercise 4.9. Let me check. I think 4.9. I put a hint of course homepage already. Exercise, that's from textbook. Okay, or homework 3. So that problem, all that's a graph we need to deal with is it may contain negative edges, but all negative edges only coming out from starting vertex S. So these are only possible negative edges. So maybe -3. So some may be positive, some may be negative. But if they're negative, these are only negative edges. So that's the type of graph we need to deal with it. So textbook asks you to prove to decide whether differential algorithm works or not. All right. Now, so the problem actually is a little bit vague. It does not really say it very clearly under what conditions that differential algorithm works for such graph and what condition it does not work. Because actually it assumes that graph has no negative cycle. Of course, you can say it does not work because such graph can contain negative cycle. So for example, if I have this one, so that's weight 1, 1. So of course, it has a negative cycle. Of course, differential algorithm does not work. You can say that's counterexample. But actually, that's not the point of this problem. This problem is ask you to decide whether differential algorithm works when there is no negative cycle. All right. Of course, when there are negative cycle, does not work. Sometimes, actually, it may be even better when the exercise contains some little problems. Then that will force you to think deeper. Now, think deeper really help you to understand the problem, to know more about the problem. So actually, I think if you have thought about it, then actually help you to understand shortest path problem better. All right. So anyway, I put that hint in the course homepage. So this one assumes there is no negative cycle. All right. Now, a fun question is, all right. Yeah, that always helps when you try to solve a problem. It's always good to start with a small example. You play with small example to get a feeling of the problem first. All right. Then you get a feeling. You will see how to proceed in order to solve the problem. Now, a fun question, it will not be in the homework, but a fun question associated with this problem is how to find the negative cycle. Using Dijkstra algorithm. So I give you such a graph. So all edges except those edge going out from S may be negative. All other edges are positive. So first, can you determine whether contain a negative cycle or not? Can you use your Dijkstra algorithm to determine whether it has a negative cycle or not? Not Bellman-Ford. Can you use Dijkstra? So that's a fun question. It's not in the homework. All right. Okay, I think that's it. Okay. So there are two more examples on dynamic programming. So I discuss either on Monday or give you a short, record a short video for that one. All right. Because next week we are going to start with NP completeness. All right. Okay. So yeah, that's it for today. Thank you. Bye-bye. Yes, that's what you want to prove, why it does not affect much. So you need to say whether the algorithm works or not when there are negative cycle. So exactly that's the point. You have to argue why it will not affect our solution. All right. Okay. Okay, some of you may want to stay for the tutorial. Okay. All right. So bye-bye.